Have you ever mixed two things together and seen all their original properties vanish? In chemistry, one of the most balanced and elegant examples of this is neutralization, when an acid and a base come together to form salt and water. In this process, the acidic property from hydronium ions and the basic property from hydroxyl ions are completely cancelled out. This reaction is exothermic, meaning it releases heat, and it has an enormous role to play, from large scale industrial processes to subtle natural balances in our environment. If you could zoom in and watch the particles during neutralization, you'd see a simple but powerful exchange. We can write it in its most basic form as acid plus base gives salt plus water. Looking closer, the ionic equation shows exactly what's going on. A hydronium ion from the acid meets a hydroxyl ion from the base, combining to make two water molecules. The leftover ions form the salt. A classic example is hydrochloric acid reacting with sodium hydroxide to produce sodium chloride or common salt along with water. Ever wondered how chemists figure out exactly how strong an unknown solution is? Neutralization is the key. In the laboratory, we use titration, a precise process that allows us to determine the concentration of an acid or base. Using a burette, a pipette, and a carefully chosen indicator, we add one solution to the other until the exact point of neutralization is reached, signaled by a sharp, unmistakable color change. For example, we can calculate the molarity of sodium hydroxide using a standard hydrochloric acid solution. From the factory floor to environmental protection, neutralization is hard at work. Imagine acidic wastewater flowing from an industrial plant. Before it's safe to release, it's neutralized. Fertilizer production relies on it, with ammonium nitrate being a prime example. Antacid tablets you buy at the pharmacy? They're tiny neutralization reactions in action, relieving heartburn. Even the air we breathe benefits. Neutralization removes acidic gases like sulfur dioxide from industrial emissions through flue gas desulfurization. You've experienced neutralization more often than you realize. On the farm, slaked lime is spread over acidic soil to help crops grow better. In your medicine cabinet, antacids neutralize excess stomach acid for instant relief. Your toothpaste is quietly fighting acids produced by bacteria in your mouth, protecting your teeth. And in nature, limestone beds and lakes act like natural antacids, buffering the water against acid rain and keeping aquatic life safe. What if I told you that neutralization doesn't just balance chemicals, it also gives off energy? Most neutralization reactions are exothermic, releasing heat that we can measure with a calorimeter. This energy is called the enthalpy of neutralization. Reactions between strong acids and strong bases release a consistent amount of heat, but when weak acids or bases are involved, less heat is produced because some energy is used first to ionize them before the reaction takes place. Let's take a moment to bring it all together. Neutralization is simply the chemical balancing act between an acid and a base, producing salt and water. At the heart of this process, hydronium ions from the acid meet hydroxyl ions from the base, forming neutral water molecules, and in doing so, both acidic and basic properties vanish. Most neutralizations release heat, making them exothermic, and this energy change can be measured in the lab. From precise titrations to large scale waste treatment, and even in the relief you get from an antacid tablet, neutralization is everywhere. It's also a key player in keeping natural and biological systems in balance, protecting our environment and our health.